When an air conditioning line starts freezing over, it is an immediate, undeniable symptom of a mechanical failure. If you hook up your gauges right now, you'll see a sharp drop in suction pressure on the low side. A common reaction is to assume it's short on gas and add more refrigerant. That's a mistake. Before you touch a refrigerant tank, you need to look at the other major variable in the system. The actual cause behind these specific symptoms is almost always a severe restriction in evaporator airflow. To prove this, you need accurate data. The strict prerequisite for testing is that the system must run under a heat load for at least 15 minutes. This gives the gases time to equalize, so your baseline numbers are reliable. Once stabilized, you need 4 specific physical tools to make an accurate diagnosis: your standard gauge set, an anemometer for airspeed, a manometer for static pressure, and a tape measure. If you skip physical airflow verification, you will misdiagnose the problem. You'll end up overcharging a suffocating system, which easily destroys the compressor. Step 1 is reading the system's current state. We check the refrigerant pressure and temperature gauges to identify the specific fault pattern the unit is broadcasting. This diagram shows the refrigeration loop. Looking left at the evaporator coil, we identify the primary indicators of restriction: low suction pressure and low superheat. An obstructed coil cannot absorb room heat, so the liquid refrigerant stays dangerously cold, failing to boil into vapor. Contrasting this with the high side of the system, the story is entirely different. Head pressure and subcooling remain completely normal, or perhaps slightly low. Looking at this gauge, the low pressure needle points to a depressed reading. This exact 4-point pressure signature definitively rules out a refrigerant leak. It proves the system has plenty of gas, but is starving for air. To find out where that air is being choked off, we use differential pressure. This allows us to measure the invisible physical resistance across the filter bank. Take your manometer and insert one probe into the ductwork immediately before the air filters, and insert the second probe immediately after them. A healthy, clean system establishes our baseline. A typical new filter creates a slight pressure drop of about 0.25 inches of water column. As the filter catches debris, resistance increases. If your reading approaches 1.0 inch of water column, you've hit the maximum saturation limit. The filters are completely plugged. There is a critical diagnostic anomaly to watch out for: a differential pressure reading of exactly 0. A 0 reading does not mean you have perfect airflow. It proves either a catastrophic bypass hole, allowing air to escape around the filter, or a complete blower motor failure. Next, we need to calculate the system's exact target air velocity, measured in feet per minute, or FPM, to establish an objective baseline. The foundational rule of thumb for cooling volume is straightforward. You need 400 cubic feet per minute of air volume for every 1 ton of cooling capacity. For a 20-ton unit, multiplying by 400 CFM gives an 8,000 CFM target volume. A 4x4 return register equals 16 square feet. Since velocity equals volume divided by area, dividing 8,000 CFM by 16 square feet reveals our target velocity, 500 feet per minute. By distinguishing raw volume from this precise FPM velocity target, you now have the objective mathematical baseline required to hunt down physical obstructions. Now we perform the physical field test. Place your anemometer directly at the face of the return register to measure the actual FPM. In diagnostic scenario A, your actual measured velocity drops significantly below our calculated 500 FPM target. We cross-reference scenario A with our manometer reading. If velocity is low and static pressure is high, the restriction is definitively isolated to dirty filters. Let's look at diagnostic scenario B. The actual velocity is low, but the static pressure is normal or even lower than the baseline. Here, the evaporator coil is choked with impacted dirt or ice. The blower pulls less air because it simply deflects off the frozen fins. Remember the most critical rule of baseline testing. Static pressure comparisons are only valid if they are established with brand new filters installed. Combining the anemometer velocity with the manometer pressure completely eliminates guesswork, mathematically proving exactly where the airflow is choking. Our diagnostic chain is complete. We verified the pressure signature, checked the filter drop, calculated the target velocity, and cross-referenced the data to isolate the root cause. Now we execute the physical fix. Either replace the saturated filter bank or physically deep clean the impacted evaporator coil.
After the fix is applied, reiterate the strict operational rule. The system must run for another 15 minutes under load to allow the refrigerant to equalize. Finally, we run our verification. Remeasure the FPM and the gauge pressures to prove the numbers have returned to their perfect operational target ranges. Treating physical airflow as the absolute prerequisite prevents you from chasing phantom refrigerant issues and ensures perfect system performance.